questions about the one mean Z or the one mean T test that we talked about last week. So I'm going to stop the share so I can kind of see your faces. You can raise your hand, type in the chat, or unmute and speak if you have questions. Specifically, I anticipate maybe you have questions about mini project 3. One of the biggest mistakes that a lot of you made, Jean and I was talking about before class started, is that at the top of the instructions in large print, it says clearly identify the data set that you have been assigned or that you are using. That means I want you to tell me that you are using either the supply chain data set or the hospital data set. Okay, I have to know which data set you're using so that I can then check your answers to the questions. And like some of you said, well, I'm using weight. Well, feasibly, weight could apply to a person and be within the hospital data, but it also could apply to the weight of a shipment. Okay, so I need you to identify very clearly at the top of the document which data set you have been assigned. Most of you did a better job identifying the variables this time. A couple of you did select inappropriate variables because you were supposed to be using quantitative and you selected qualitative. The other issue that popped up a good bit was you calculated a Z interval when you should have been using a T interval. Guys, none of you, whether you had the supply chain data set or whether you had the hospital data set, you did not know the population standard deviation for any of those variables. In fact, if you look at the instructions where I had you tell me the sample size, the sample mean, and the sample standard deviation, I even had it on the paper that you had the sample standard deviation. You have to use a T as in tiger interval when you only know the sample standard deviation. And in the real world, and in most cases, you're going to have to use a T interval because we've talked about how difficult it is to get information from every single item in the population. It is rare when you are conducting real world research that you are going to know the population standard deviation. Therefore, you should use a T interval. Similarly, for the one mean Z test and the one mean T test, you use Z as in zebra whenever you know the population standard deviation. Again, in reality, that is very rare. In most cases, you're going to only know the sample standard deviation, and therefore you would do a one mean T as in tiger hypothesis test. Now, that statement is going to be important as you begin to think about mini project number 4. You should use, you do not know the population standard deviation for any of the variables in either of the data sets that you have. And therefore, you should use a one mean T as in tiger test not Z. I cannot make it any clearer than that. Okay, any questions on normality before we move on?
Yes, I just want a clarification about mini project 3. So if I understand what you're saying is that the number one question is just to state which data set we are using, and that's it.
No. It is not actually a question. It is part of the header in bold print. Let me see if I can pull it up so you can see it. In bold print in the header, clearly identify the data set assigned to you. So right there in that spot, you need to tell me that you either have the supply chain data set or you have the hospital data set. Then in question 1, you have to identify a quantitative variable from the data set that you have identified in the header. Sadhu, do you understand?
Yes, okay. So for example, if I'm using a line, the quantity variable line, so I have to state that element I'm using right there on number one question.
Yes.
Okay. And I have another question too on number 7. I don't really understand what I'm supposed to do on that, on mini project 3.
2 and 7?
No, 7, just a 7.
7 is basically you're going to copy the Minitab results. Okay, it says copy and paste the probability plot from Minitab. So when you run Minitab, and let me see if I can pull in a data set. It doesn't matter which one I pull in. Okay, hold on, I have to choose a different option. Okay, so let's say we're looking at loan applications. I just pulled in a data set. It doesn't matter which data set I use. I need a quantitative variable. So let's say I look at the income for the loan applicants. So when I run the normality test on that variable, really what I need is this entire thing here. Okay, this graph is called a probability plot. Okay, so I would paste, I copied it, and then I'm going to paste it into the document. That pasting also covers question 4 because on this same display, you have your Anderson-Darling and your corresponding p-value. So this one plot, which is the Minitab results, covers question 4 and question 7.
Okay, that's why I'm confused because I had it already on question 4, so I didn't know I had to do the
well,
same.
you don't have to
thing
do it twice. I probably wanted to make sure you had the plot on here. So okay. I tagged that at the end. So you got to have that plot on there. I'm going to be looking for this display, which has the probability plot as well as the Anderson-Darling and p-value. And guys, it's more than just copying and pasting. Do you understand what the word record means? Record means to write it down. You don't simply just copy and paste. You need to write it out. You need to say the Anderson-Darling test statistic is 1.14 and its p-value is 0.005. It's not just copy and paste. Guys, you've got to think about, if you're writing a report, you're not just going to copy and paste a picture in there. You have to offer an explanation. Now, granted, sometimes that explanation is under the graph itself, and other times it's written into in paragraph form or sentence form, and then you're referred to the graph. If you don't learn to follow instructions, guys, you're not going to go very far in life. That's part of your education. And some of you are having a very difficult time doing that, to be honest. Don't wait till the last minute. I've detailed out the instructions and told you exactly what to do. Other questions related to number 3 before we move on? Okay, so tonight we're going to look at 2 mean t-tests. Now, in the course for Business 3000, we are still in Module 3. We're still on the topics 1 mean and 2 mean test, Mann-Whitney, Wilcoxon, and Cohen's D. Last week, we covered 1 mean. And this has taken a long time to load the last few days, so give it just a minute. Usually I have to go off of it and come back to it. Okay, but I've posted on that page PowerPoints for 2 mean t independent test and the paired t-test. There's one for Mann-Whitney U and one for Wilcoxon signed rank. Okay, so there's 3 different PowerPoints. There are also Word documents. Okay, so we had last week, we had the 1 mean hypothesis testing PowerPoint and the examples, which were in Word format. You also have 2 mean PowerPoint with examples in Word format. Mann-Whitney U PowerPoint with the data set that you need, and Wilcoxon signed rank PowerPoint with the data set that you need and the examples in a Word document. So if you follow along using these PowerPoints, you may want to open 2 mean t, Mann-Whitney U, and Wilcoxon signed rank, because we're going to move between them tonight. So beginning with the 2 mean t-test. Again, last week we focused on 1 mean. This week we're going to focus on 2 mean. Now, these 2 mean tests are parametric tests, just like the 1 mean test were parametric tests. Remember, parametric test, it means that we are comparing the mean of those things, of the populations. We're comparing the means, but we're making 2 pretty big assumptions. One, we're assuming that we have a normal distribution, and 2, we're assuming we have equal variances or equal standard deviations. So those are 2 pretty big assumptions. Again, if our sample size is large enough, we can force any distribution to be normal by applying the central limit theorem. So just be aware of that, because what we're going to do tonight is we're going to look at the parametric test, and then right behind it, we're going to look at the non-parametric test. Okay, in most cases, for each parametric test, which analyzes the means with the assumption of a normal distribution and equal variances, there is a comparable non-parametric test. Non-parametric test looks at the relationship between the medians, and we do not have to assume or know that we have a normal distribution or that we have equal variances or equal standard deviations. So we're going to look at both. Okay, so we're going to look at parametric and then non-parametric. There are two different mean t-tests that we're going to look at. And guys, you are going to have to make a decision when you're working through quiz 8 and when you get to your final as to which test you need to conduct. Whether it's a one mean Z, one mean T, two mean T, paired T, Mann-Whitney, or Wilcoxon signed ranked. You are going to have to make that decision. That decision is based upon the information that you have. And so you're going to have to read carefully and pay very close attention to the details. So one of the tests that we're going to focus on is what they call an independent sample t-test or an independent t-test. With an independent t-test, it is parametric, so we're comparing the two population means. Instead of just looking at one, we're now going to look at two population means. We use an independent sample when we want to compare, or independent t-test, excuse me, an independent t-test whenever we want to compare two different groups to see if they follow the same trend or the same pattern. Okay, so basically you're going to have one variable, one thing that you're interested in, but you're going to collect information from two different groups. For example, you might look at the football team scores. So your interest is the scores, and you may look at it for, say, Calhoun High School and Cartersville High School. Or you might look at it for the Atlanta Falcons and the San Francisco 49ers. Okay, so you're looking at the score, so it's one score, but you're looking at it for two different groups. It could be exam scores. I could compare the exam scores for my class that meets at 9:30 to the exam scores for the class that meets at 12:30. I'm looking at the scores, that is my variable, but I'm doing it for two different groups. Independent is one variable, two groups. And just as a side note, for part of the calculations, we do not pool the variances. We do assume the variances are equal, but we do not pool them or group them together. And that's just a little side note. It's technical and we're not going to get too detailed about it. The other two mean t-test is a dependent t-test, or it's usually called a paired t-test. With a paired t-test, we actually look at the difference between one variable from one population taken at two different points in time. So for a dependent test, you have one variable, one population, but you've collected data at two different times, kind of like pre-test, post-test. I could look at the scores at the beginning and the scores at the end, pre-test, post-test, for one class. We could do the scores for a football team before and after. Think about Georgia Tech. They just recently, a few weeks ago, fired their football coach. So we could look at, the scores before the coach was fired and then after the coach was fired. Okay, so again, you're looking at the scores for one team, but you're looking at it before and after. So we're going to focus first on the two mean independent t-test. Okay, we're going to focus on that. When you're thinking about the independent t-test, your independent samples, remember, you're going to collect information about a single variable from two different groups. And we assume that we do that using a simple random sample method, meaning that every item in the population had an opportunity to be selected. If the sample sizes are small, okay, this is kind of where we get into, it's got to be normal, that kind of thing. If the sample sizes are small, we have to know that the distributions are normal. Do you remember, typically small is less than 30. If you have a large sample, we don't necessarily have to assume that they're normal because I can apply the central limit theorem. Okay, I have on the screen so that you can write them down, print it out, whatever you want to do, the mini-tab instructions for a 2-sample T independent test. And these questions can be presented in two different ways. One, it can give you summarized data, or the other format, you can be given the raw data. And we're going to try to take a look at each type. This particular set of instructions is for summarized data. You can see that in the header of that slide. Okay, so I have a test here, and I'm going to go out to my Word document where I have these in Word so that we can talk through it. Okay, this is on the Word document that you have in D2L, and it says, a study is done by a community group in 2 neighboring colleges to determine which one graduates students with more math classes. College A samples 11 graduates. Their average is 4 math classes with a standard deviation of 1.5. College B samples 9 graduates. Their average is 3.5 math classes with a standard deviation of 1. The community group believes that a student who graduates from College A has taken more math classes on the average, and both populations have a normal distribution. Test at a 1% significance level. Now, if I had not told you that this was a 2 mean independent t-test, and this was a question that you might see on your quiz 8 or on your final exam, you would have to be able to identify it. So a couple of things jump out at me as I read through this problem. One, it starts out talking about 2. So I've got 2 means or 2 groups. So I know that I have 2 populations. And it says, want to determine which one graduate students with more math classes. So my variable here is the number of math classes that a student takes. Okay, so I'm collecting data, and if I continue reading, it gives me the data. Okay, one variable, the number of math classes from 2 different populations. The other thing that's important to me is near the end here where it tells me that we have a normal distribution. The fact that I have 2 populations with 1 variable and I want to compare them, and I have a normal distribution, is what allows me to conduct a two-mean independent t-test. Now, the process for this test is the same 5 steps that we've been doing for what seems like forever. The first step in any hypothesis test is to state the hypotheses. Remember that the null must contain equal in some form, and the alternative does not contain equal in any form. So if I'll go back through and look at this problem, it says the group believes a student who graduates from college A has taken more classes on the average. So they're saying that, and it might help you to put it in here and say on average than college B. So we're comparing college A to college B, and it says that A has taken more. So I see that word more makes me think of the greater than symbol. Since I have the greater than symbol, that statement is my alternative hypothesis. Now we have to write it a little bit differently. We have to say that the mean for college A is greater than the mean for college B. And honestly, that's what that statement that I've highlighted in green is saying, that a student, or the mean number of classes taken by students at college A, is more than those at college B. So this is the given. So by default then, my null hypothesis is the mean for A is less than or equal to the mean for B. We use subscripts. You could label them 1 and 2. Since they have it as A and B, I'm using A and B. I will tell you that Minitab just uses sample 1, sample 2. So, if you want to make yourself a note off to the side, in this case, sample 1 is college A, because you want to make sure you're consistent, and sample 2 is college B. Again, Minitab only uses the distinction 1 and 2. Okay, so we've stated our hypotheses. Step 2 is to identify the players. And in this case, I'm going to have information for college A, and I have information for college B. And again, just as a side note, in this scenario, you have summarized data. It's summarized, 1, because I don't see a list of data anywhere, but 2, it tells me the sample size, the sample mean, and the sample standard deviation for each college. And so I'm going to write that down. So if I go back and look at my sentences, okay, it says college A samples 11 graduates. Their average is 4 math classes with a standard deviation of 1.5. So I can write all of that information down. It says they sampled 11 graduates, got a mean of 4, and a standard deviation of 1.5. If I continue reading, it says college B samples 9 graduates, and their average is 3.5 with a standard deviation of 1. So college B, there were 9 sampled. We got a mean of 3.5 and a standard deviation of 1. The other piece that I need is my level of significance, which is in the last sentence, and it says to use 1%, which is 0.01. Now, by default, then my confidence level is going to be 99%. Remember, significance level plus confidence level has to total to 100. So step 3 is to calculate the test statistic, which in this case is going to be a t, and its p-value. But again, guys, we don't do that by hand. We use the technology that we have been blessed with, and we use Minitab to perform these calculations. So we're going to go out and do that. So I have Minitab pulled up. I'll get a fresh, clean project. Okay, so we go to Stat, Basic Statistics. This is a 2-sample T. We have summarized data. And now you can kind of see why I created that table there when we were identifying the players, because it's set up very much like Minitab. For college A, which is sample 1, there were 11 in the sample with a mean of 4 and a standard deviation of 1.5. Sample 2, or college B, there were 9 in the sample with a mean of 3.5 and a standard deviation of 1. So I basically have entered all of that information that I had summarized into a table form that I pulled out of the scenario. I choose options. We are using a 99% confidence level. My hypothesized difference defaults to 0 every time. And we are saying that college A is more, and we always assume equal variances. I click OK. I click OK. Now, Minitab gives me a fair amount of information, okay? It does give me the descriptive statistics that I summarized for it, okay, that I had for sample 1 or college A. There were 11 with a mean of 4, standard deviation of 1.5. Sample 2, so it gives me that. It also gives me what's called the estimation for difference that we looked at the other night. And then finally, what we really need is the results here under test.
Quick question. I don't mean to interrupt.
Go ahead.
Okay, so are we always saying that there's not an equal in the alternative hypothesis?
There is, in all of the hypothesis testing that we focus on, there is never an equal in it. Now it can be less than, greater than, or not equal, but there will never be an equal in the alternative hypothesis.
Right,
never,
thanks.
ever. Okay, so here's my results. My T is 0.85. So this is the record part. T is 0.85, and the p-value is 0.202. So I have recorded my test statistic and its p-value. Step 4 is we make a decision. We make a decision by comparing the p-value to the level of significance. The p-value comes from Minitab, which is 0.202. The level of significance is given in the problem and was 0.01. We compare those two values digit for digit. The first number after the decimal and the p-value is 2. The first number after the decimal and the level of significance is 0. 2 is greater than 0, so the p-value is greater than the level of significance. When p is greater than the level of significance, we always reject the null hypothesis. The last step in the hypothesis test is to write our conclusion. So let's think through what this means so we know what to write. Based on the evidence that we were given, we have determined that we are going to reject the null. If I reject the null, that means the null is false or invalid. And therefore, by default, the alternative statement is true or valid. And so in this statement, what we have proved is that the student who graduates from college A has taken more math on the average than a student who graduates from college B. So I have to write my statement so that it says that. Now there's a variety of ways that you could say it. You always include your level of significance. So I would say at the 0.01 level of significance. Jada, go ahead. Jada. Jada, I see your hand raised. Do you have a question? Jada, do you have a question? I can't hear you, hun. Can you type it in the chat, Jada? Oh, did I get it wrong? Oh, you're right, Jada. Thank you. My fault. My fault. Thank you, Jada. Okay, Jada's right. I got it wrong. When P is greater than alpha, we fail to reject. I'm sorry. That's my fault, guys. I got excited. Okay, so let me go back up here and correct my mistake. That's my one for the night. Okay, so Jada's right. Because P is greater than alpha, we fail to reject the null. If you fail to reject the null, that means that the null is actually true or valid. And by default, the alternative is false or invalid. So in this case, what we really have
proved the screen.
Okay, thank you. I'm sorry, I took it off. Now, can you see it?
Yes, thank
okay.
you.
I'm sorry. Okay, so again, the p-value is greater than alpha, and so I should have failed to reject the null, which means the null is true. And the null says that a student who graduates from college A has taken less math than those at college B. Okay, so let me scroll back down here where I can write my conclusion. Again, when you write your conclusion, you always include the level of significance. So at the 0.01 level of significance, a graduate from college A has not taken more math on the average than a graduate from college B. Now, again, there's other ways you can say that.
And really what we're doing is we're rewording the question, right? For the conclusion.
You are basically using the question in the conclusion, but you always state the conclusion in terms of the hypothesis that is true. So in this case, I had to add the word not because the original statement said that they had taken more, has taken more, but what we proved was they had not. So I had to add the word not so that my conclusion is always stated in terms of the true valid hypothesis.
All right, I'm just kind of confused because it says that if the p-value is greater, then that means it's not rejected. So that means that the statement would be true. That's why I'm kind of confused on why you added the not in there. Because I thought we were trying to prove that, yeah, that what's in green is what we're trying to prove in the null hypothesis. And
No,
so
sir.
the not, okay.
No, sir. The statement that is highlighted in green is my alternative hypothesis. My null hypothesis is that college A takes less than or equal to college B, which is not more than. Jean.
Yeah, I'm listening. I'm still just trying to process it to make it make sense. Because, like, okay, so the question itself is the alternative. I understand that part. So that's why you added the not, because what? That didn't really make sense to me, is what I'm trying to say. Because if it's greater than, then we're supposed to reject the null, or we do not reject the null, which would make the hypothesis true.
But no, you're not. You're confusing two things.
Okay.
My hypothesis is that a student who graduates from college A has taken more math classes than a student from college B, which is the alternative hypothesis.
Okay.
By default, then, the null hypothesis, which is the exact opposite of the alternative, is that the mean for college A is less than or equal to college B. Throughout the hypothesis testing process, I assume that my null hypothesis is true. So I have assumed that college A takes less than or equal to college B. I've assumed that that is true. I run my test. Based on the probability value, the p-value that corresponds to my test statistic, which is calculated from the data that I was given, my p-value is greater than the level of significance. The fact that that p-value is greater than the level of significance has absolutely nothing to do with the fact that there is a greater than in the alternative hypothesis. That's what you're
Okay.
confusing.
Yeah,
Those are
because I
two
don't.
completely different things.
So in the question, I'm given the alternative.
In this question, yes.
Okay.
But
All
now the
right.
next question, you could be given the null. Sometimes you get the null. Sometimes you get the alternative. You have to pay attention to the verbiage.
Right. That, I think that's what threw me off.
Okay. All right, so let's move on to another example. It's still a two-mean t-test independent, but the difference is in this particular problem, you are given the raw data. See, the difference is I have the list of data. It doesn't tell me we had this many in the sample and a sample mean of this and a standard deviation, okay? So I have the raw data. Now, in D2L, or excuse me, on the PowerPoint, I have the raw data, the instructions on how to deal with the raw data. Okay? But before we do that, I need to backtrack just a minute. Okay? Typically, after you do a two-mean t-test for independent samples, there is what we call a post hoc test. Okay? That post hoc test is just basically means we're going to do an additional test after the one that we did to start with. So it's kind of like we've done the first analysis. We're going to go one step further. And that post hoc test is called Cohen's D. It's named after the United States statistician Jacob Cohen, who kind of developed it. And it's a way to measure what they call the effect size. The p-value that we've been using throughout this hypothesis testing process tells us whether there is an effect. You know, in this case, is there a difference between the number of math classes taken by students at college A versus the ones taken at college that are at college B? Okay, so it tells us there is an effect, and whether that effect maybe is less than, greater than, equal, not equal. But it doesn't tell us how large the effect is. Is it, is it just a, just a minor, kind of think about it like, is it just a minor effect or is it a really big effect? And so Cohen's D, which is a post hoc test, is always reported whenever you do a two-mean independent t-test. And what it does is it measures, it gives us a measurement, or a quantifies a quantity of the strength of the differences between the means of the two populations. It literally looks at the relationship between the two means and kind of says, well, this is a, kind of a weak relationship. It's a strong relationship. Cohen set up some standards and he used the terms small, medium, large. Okay. I suppose you could talk about weak, neutral, strong. Okay. But it should always be reported with the independent t-test. It is actually one of the few manual calculations that you have to do. It's a very straightforward formula, and all the information you need to calculate it is provided in Minitab. Okay, so the formula is you take the difference between the two means and divide it by the pooled standard deviation, and you can see it there on the screen. Sometimes that value is going to be negative, sometimes it's going to be positive. And then depending upon its value, we come back to this table, and this table is provided on the quiz and on the final exam so that you don't have to memorize it, but come back and we think about whether we have a small effect or a large effect, medium or large. Okay, so let me show you how to do this. So we concluded that students from college A had taken less or fewer math classes on average than those from college B. Okay, so there obviously must be a difference. What kind of effect is that difference? Is it small, medium, or large? So for this independent t-test, we have to go one step further and run the post hoc test, which is Cohen's d. And again, the formula for Cohen's d is we look at the difference and we divide it by the pooled standard deviation. And again, all of that information we actually have already been given in Minitab. When I calculated this test, the 2-sample t-test, if I scroll back up under the header, estimation for difference, you'll see, and I'm going to copy it where we can look at it. It gives you the difference and it gives you the pooled standard deviation. I just got to plug and chug. Okay, I have the formula for Cohen's d, so I have my difference is 0.500 divided by the pooled standard deviation, which is 1.302. Both those numbers are given in the Minitab output. Now I do have to manually calculate this with my calculator. So 0.5 divided by 1.302 equals approximately 0.384. Okay, so Cohen's d for this particular test is 0.384. Now, if I come back over here to this table on my PowerPoint, you may be scratching your head because you're going, well, Miss Ralston, it's not 0.2 and it's not 0.5. It's between 0.2 and 0.5. Okay, so I'm going to make a statement here. 0.384 is between 0.2, which is a small effect, and 0.5, which is a medium effect. Okay, we round down. So in this case, there is a small effect. Okay, our conclusion would be there is a small effect, meaning that difference is really not that big. We concluded that college B takes more math than college A, but it's really not a big difference because there is a small effect. Okay, so you calculate your Cohen's d, see where it falls, and we round down. And anytime you do an independent t-test, you need to calculate Cohen's d. Okay, moving on then. A teacher believes that her 8 a.m. class doesn't perform as well as her 11 a.m. class on the final exam. At the 5% level of significance, is there a difference between her 8 a.m. and 11 a.m. classes? So again, you would have to recognize that this is a two-mean independent t-test. So think about it. You've got an 8 a.m. class and 11 a.m. class. If that's not obvious enough, you have a table with two columns. So again, I have two populations, and my variable is the final exam score. Now, it doesn't tell me. I could analyze it to find out for sure, but I'm going to make this statement. The distributions for both classes are normal. Remember, we need to know that we have a normal distribution, and we could analyze that using the Anderson-Darling test, okay? But I'm not going to go into that detail. So again, we're doing a hypothesis test, guys. The first step in any hypothesis test is to state the hypotheses. Okay, so you have the null hypothesis, which must always contain equal. And you have the alternative, which does not contain equal. So if I read, it says, is there a difference between the 8 a.m. and the 11 a.m. classes? Okay, so my keyword here is difference, which makes me think they're not the same, which would be not equal. And since I'm using not equal, that statement is my alternative hypothesis. Okay, so the mean for the 8 a.m. class does not equal the mean for the 11 a.m. class. That's the one that's given. The null hypothesis is the exact opposite. So it would be that the mean for the 8 a.m. class is equal to the mean for the 11 a.m. class. So I am considering the 8 a.m. class as sample 1 and the 11 a.m. class as sample 2. Again, that may help me keep it straight when I go into Minitab. Step 2 is to identify the players. And I'm actually going to write that right up here because my players in this particular case is this raw data. Okay, in this case, you have raw data. The only other piece you need is your alpha, and it says to use 5%, which is 0.05. So I'm down to step 3 in the hypothesis test, which is to calculate the test statistic, which is a T, and its p-value. And we're going to do that in Minitab. This time, though, I do have to enter that raw data into Minitab. That's all the information I have, and so I have to use what I have. So in column 1, I would put the final exam score 8 a.m. In column 2, I can put the final exam score for the 11 a.m. And I would type the data in. Okay, let me get it here where I can see it. Okay, so I entered the ones for 8 a.m. and I'm going to go back and enter the data for 11 a.m. Okay, so I have entered the data. So I'm going up to Stat, Basic Statistics, to Sample T. This time I have each sample in its own column. Sample 1 is the 8 a.m. class. Sample 2 is the 11 a.m. class. We're using a 95% confidence level. My hypothesized difference is 0, always. This time we're doing not equal, and we still assume equal variances. I click OK. OK. Now, one of the things that Minitab does, that if you needed it, it does give you a summary. It tells me that I had 9 data values. The mean was 56.6 with a standard deviation of 22.1. It also does the same information for the 11 o'clock. So it does the descriptive statistics at the same time should you need them. I have the estimation for difference that I may need in a minute to do Cohen's d. But initially, I need my t-test statistic and its p-value. So I then have to write it down. My t-test statistic is negative 2.34, and the p-value is 0.033. I'm at step 4. Step 4, we make a decision. We make a decision by comparing the p-value to the level of significance. My p-value, which I get from Minitab, is 0.033. My level of significance is 0.05. Again, make the comparison. First digit after the decimal, they're both zeros. Second digit for the p-value is 3. Level of significance is 5. 3 is less than 5. So p is less than or equal to the level of significance. When p is less than or equal to the level of significance, we do reject the null. I think I got it right this time, Jada. Now, again, thinking about what that means. If I reject the null, that means the null is false or invalid. And by default, then the alternative is true or valid. So in this particular case, based on the data that we have, it appears that there is a difference in the mean final exam scores. So step 5 is to write a conclusion. Again, your conclusion should always include your level of significance. So at the 0.05 level of significance, there is a difference between the mean final exam scores for the 8 a.m. and the 11 a.m. classes. Okay, so there is a difference. It's an independent t-test, so I have to go one step further and run the post-hoc test. The post-hoc test is Cohen's d. Again, it is the difference between the means divided by the pooled standard deviation, which we have already found in our mini-tab results, going back out to get them, under the header, estimation for difference. So I'm plugging and chugging. My difference is negative 20.33. The pooled standard deviation is 18.45. I'm going to do that division. Negative 20.33 divided by 18.45 is negative 1.102 when I round it. Now, guys, you got to be careful here, okay? Then I've got to compare that to the value on the table. Well, negative 1.102 is less than negative 0.8, which was the large effect. Okay, so because it is less than, it's less than because it's negative, okay, we would conclude there is a large effect, meaning there's something really weird going on because there is a significant large difference between the mean for the 8 a.m. class and the mean for the 11 o'clock class. And if I'm the instructor, then I'm going to start thinking about, what's different. Are the students still half asleep at 8 o'clock? Am I teaching it differently? That then gives me a place to start looking at or doing further research and thinking about why there is such a large effect. Questions?
Where's the 0.8 coming from?
The Cohen's d table.
Oh, okay.
Other questions? Okay, so that is the two mean independent t-test. That is a parametric test where we are comparing the means, but we are assuming we have a normal distribution and that we have equal variances. But what if I don't have that? When we do not have, or we are not able to make the assumption that we have a normal distribution or that we have equal variances, we then have to think about or consider using a non-parametric test. A non-parametric test looks at the medians. The test the non-parametric test that is comparable to the two mean independent t-test is the Mann-Whitney U, or it's also called the Wilcoxon rank sum test. Now we use the term Mann-Whitney, but the Mann-Whitney again is a non-parametric test that's going to compare the means the medians of two independent groups. So you still have that one variable and you collect data from two different groups, but you can no longer assume that the distribution is normal or that you have equal variances. So I cannot use the two-mean independent t-test. So the Mann-Whitney U-test helps us to test whether the two samples come from the same population or they at least have a similar shape, have the same shape. We still have to assume that we have simple random samples, that every item in the population had a chance to be selected. Again, we still, ideally, if we have a small sample, we want to think about the distribution, but it doesn't have to be normal if we're using the non-parametric test. If we have a large sample, again, we could use the central limit theorem and force it to be normal, or we can run the non-parametric test. I will tell you that if we can, statisticians prefer to run the parametric test because the parametric test tend to be more powerful. You get better results. But that's not always possible. So for our purposes, we're going to focus on using Mann-Whitney U whenever we have the scenario where our distributions are not normal. It's hung up on me. All right, I have to stop the share and go out here and okay, so let me start the share again. Now, there are 4 assumptions that we make with the Mann-Whitney test. Okay. The first assumption is you have one dependent variable that is measured at the continuous or the ordinal level. So let me kind of give you some examples here of what that is. Okay. The dependent variable, that would be like your output or your y, is continuous or at the ordinal level. If you're thinking about continuous, think about things like time, weight, IQ scores, even exam scores. Those things are on a continuous measurement scale, or things that are ordinal, that can be ordered, like the Likert scale that you often see on surveys that has strongly agree, neutral, disagree, strongly disagree. Okay, that kind of that level. Or even think about like movie ratings, where you have, you know, hated it, so-so, loved it, best movie I've ever seen, those kind of things. Those are ordinal levels. You have one independent variable, but you have 2 groups. Okay, so you have 2 categories. Again, they're usually dichotomous, meaning 2. So think like gender, employment status. You could do employed and unemployed. You could do smoker, non-smoker. You could do things like yes or no. In a clinical trial, it might be placebo or actual medication. So you have kind of 2 categories. You have an independence of observations. Again, the selections for the first group do not affect the selections for the second group, or what happens in the first selection doesn't affect the second selection. We've talked about that before. And the last one, and there's some words missing here, I discovered this morning. I'll have to plug them in here in a minute. You must determine whether the distribution of the scores for both groups of your independent variable come from the same distribution, the same population, or the same shape distribution, or have the same shape. I think I actually corrected it on the slide a little bit later. Now, again, most of the times in this course, we can assume those, those assumptions are true. I'm going to walk you through that in one of the examples here in just a minute. A lot of this information that we're talking about in relationship to Mann-Whitney is not in the OpenStax textbook. And so I have the link there to where this information was found, the source. And so I want us to take a look at an example of the Mann-Whitney U-test. And this one is on the Word document that I did post in D2L, so you would have access to it. It also tells you in that problem that the data set is provided in D2L. Okay, so I had to give you the data set. So the questions reads, a state highway department uses 2 brands of paint for painting stripes on roads. A highway official wants to know whether the durability of the 2 brands of paint are different at a 5% level of significance. For each paint, the highway official records the number of months the paint persists on the highway. The distribution for both brands of paint are not normal. The data set is provided in D2L, and I'll tell you the name of the data set. Now, here again, I've told you in this discussion that this is a Mann-Whitney U. But when you go to do your quiz 8 or to do the final, you're going to have to make that decision yourself. So again, let's take a look at this. One of the first things that jumps out at me is that the distribution for both brands of paint are not normal. Okay, that's the biggest clue that I'm going to use a non-parametric test. That's kind of the defining line for us in this course. But then if I keep reading, if I go back and look at the beginning of the story, it says it uses 2 brands of paint. So again, I have 2 populations. Okay, because I got 2 brands of paint. And what I'm interested in, the variable, is they call it the durability, but it's how long the paint lasts. Okay, so again, I have that one variable, but I'm looking at it for 2 different populations. And those populations are not normal, which is the big clue that I'm going to do the non-parametric test and that I need to use Mann-Whitney U. Okay, so again, as is the case for any hypothesis test, we have to state the hypotheses. It is still true, even with the non-parametric test, that the null will contain equal and the alternative will contain no equal. So this one says the official wants to know whether the durability of the 2 brands of paint are different. Okay, whether they are different. Again, I see that word different, and that to me means they're not the same, which means they are not equal. Now, it just says I got 2 brands of paint, so it could be brand 1, brand 2. I happen to know that in the data set, they call it brand A and brand B. So what we're saying here is that the median for brand A does not equal the median for brand B. The other difference, the fact that we're doing a non-parametric test, means we're comparing the medians, not the means. So that's why I had to write the word median there. We don't have a fancy symbol for median. This is the one that's given. So the median for A is equal or the same as the median for B would be my null, again, because they're opposite of each other. Okay, step 2 is still to identify the players. The players here is the raw data in the data set that's given. Okay, and I haven't pulled that up yet. I will in just a minute. The other piece that we need, of course, whenever we're conducting our hypothesis test is our alpha, and I believe it said 5%. Yeah. So alpha equals 5% or 0.05. Third step in the hypothesis test, which hasn't changed, is we calculate the test statistic. And it's going to seem weird, but the test statistic here is a W. Remember that Mann-Whitney U is also called Wilcoxon ranked sum. Okay, so the W comes from the fact that it could be called Wilcoxon and its p-value. And again, to do this, we are going to use Minitab. So I'm going to upload to Minitab that data set. Now, I already have it on my desktop. So I'm going to open a worksheet, and it's called Highway Paint. And Minitab pulls it in. And what I have here is the number of months that the paint lasts on the highway that was recorded by the highway official for brand A and brand B. You'll also notice if you scroll down, we have 11 values for brand A and only 10 for brand B. It is okay. You don't have to have the same number of values. All right, so here we go. We're going to do Mann-Whitney. And I do have on the PowerPoint somewhere the steps. Okay, so I have stat. Then I've got to scroll to the bottom. There's an option that says non-parametrics. So I'm going to choose non-parametrics and then Mann-Whitney. My first sample is brand A. My second sample is brand B. We're using a 95% confidence level, and we're saying that there is a difference or they are not equal. Now, if I needed to, I could choose one of the others, but I'm doing not equal. I click OK. Again, Minitab does a variety of things. It actually does calculate the median for each sample. It gives me the estimation for difference if I needed it. What I need is the test results. Okay, in this course, we use the top row that's not adjusted for ties. What Mann-Whitney does is it takes all of your data values and it ranks them, like puts them in order. this one's first, this one's second, this one's third. And so if there's two values that are the same, so that if they're tied, it will make an adjustment for that or not. And so we use the option for not, okay? And so we record our W test statistic, which is 76.50, and the corresponding p-value is 0.002. Step 4 is the same step we always have. We make a decision. By comparing the p-value to the level of significance. The p-value comes from Minitab, 0.002. My level of significance comes from the problem, which was 0.05. We compare the two. First digit after the decimal, they're both 0. Second digit, I have 0 for the p-value, 5 for the level of significance. 0 is less than 5, so p is less than or equal to alpha. When p is less than or equal to the level of significance, we do reject the null hypothesis. Now, in this context, let's think about what that means. Okay, again, if we reject the null, that means that the null is false or invalid, and the alternative is true or valid. So we have actually proven that there is a difference in the durability of the two paints because the median values are not the same. Okay, so the median values are not the same. So we would write our conclusion. That's our last step. Okay, again, you want to do that. Make sure you do that with using your level of significance. So we would say at the 0.05 level of significance, there is a difference in the durability of the two brands of highway paint. Now, it doesn't really tell us necessarily which one is different. We could get a sense of that if we go back and we look at our statistics. It looks like the median for brand B is higher, which means brand B lasts longer than brand A. Okay, but we haven't necessarily proven that. We've just proven that there is that difference. Okay, so that's Mann-Whitney. Do you have questions? I've got 29 minutes, and I want to try to at least get through the paired t-test because I looked at quiz 8, and I know that there are some paired t-tests on the quiz. So I want to try to get through this one. We may not get to Wilcoxon tonight at least. Okay, but I did not see any Wilcoxon on the quiz. Okay, so I'm going back to a parametric test. Okay, so we looked at independent two-mean t-test, which is parametric. We've looked at Mann-Whitney U, which is the comparable non-parametric. Okay, so that's finished. We're going back to the parametric test, and we're going to look at what is typically called the paired t-test. With a paired t-test, you have one variable, one thing that you're looking at for one population at two different times. This is your before and after, pre-test, post-test. We could do year 1 to year 2. Okay, so you're looking at one variable from one group at two different times. And so again, we want to ensure when we're doing that, that we are using simple random sampling, obviously, meaning everybody in the group had the opportunity to be selected. Oftentimes with a paired t-test, our samples are small. We take two measurements, two samples from the same set of individuals, again, at different points in time. We then calculate those differences, okay? And those differences actually become the data or the sample that we're going to focus on. Okay, so it's almost like a three-step process. Okay, so I'm going to collect data from, let's say, the pre-test, and I'm going to collect post-test information, and then I'm going to compare those. So comparison, or the difference, means we're going to subtract them, and we end up with some number. We get that difference, and that list of differences become our sample that we actually analyze. So we're actually analyzing the mean of the difference between the two measurements. The symbol that we use for that is the mu, which is the mean, with a subscript of d, which is the difference. Okay, whoops, I skipped something. Now, again, to use the parametric test, we have to assume that our population is normal, or again, we have a large enough sample that it can be approximately normal, or we can apply the central limit theorem. But again, oftentimes with a two-mean t-test, you're dealing with, or paired t-test, excuse me, you are dealing with small samples. So you have to be careful about that. I then have on the next slide, these are the keystrokes. And typically with the dependent test, we're often only given the raw data, or you may only be given the differences. Okay, I believe in the ones that I have seen that were on quiz 8 and the examples we're looking at, you are actually given the raw data, not the differences. Minitab will do the differences behind the scenes in the calculation. Okay. So it says, again, I've told you it's a two-mean t-test or paired t-test, but I'm going to walk you through how you know. A study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown in the table below. A lower score indicates less pain. The values are before and after hypnosis. The before is matched to an after value, and the differences are calculated. In this case, the way you would read this is subject A reported a level of 6.6 before hypnosis and a level of 6.8 after. Okay, they're paired in the sense that the values are for the same person. Okay, so the before and after, and the differences are calculated. Now, it doesn't show the differences on this table. Again, that is something that Minitab is going to do for you behind the scenes. The differences have a normal distribution. Are the sensory measurements on average lower after hypnotism tested a 5% level of significance? Okay, so one thing that jumps out at me initially here is that it tells me that the differences have a normal distribution. When I have a normal distribution, I know that I can use the parametric test. It's somewhat obvious because of the display. I kind of hope that the display here maybe gives you that sense that they are paired together. But again, if you think about this, you have the list of subjects. Your variable is the pain level, okay? And your population is the patients, and we're looking at them at two different times. You're looking at them before and after. Again, so that kind of helps me. I have one variable, one population, but two measurements taken at different times. That's the clue that this is a paired t-test. And again, the fact that it's normal lets me know that I can do that parametric test. Okay, so we begin the hypothesis test like we always do. We state the hypotheses. We have the null, which must contain equal, and we have the alternative, which does not contain equal. And you got to be really careful here, guys. You got to pay attention to how this is worded. It says, are the sensory measurements on average lower after hypnotism? So it's important to note that it says after hypnotism, because that means that your after technically is your sample 1. Because I'm interested in knowing what happens after hypnotism. So that becomes my sample 1. And so by default, the before is my sample 2. Now, it may not always be that way, guys. You got to pay attention to the verbiage and the words. It is so important that you read these problems word for word for word. Okay? So, this says, are the sensory measurements on average lower? So I'm thinking lower, the word lower mathematically makes me think of less than. And if it's less than, that means this is the alternative. So we're saying that the mean difference of the after and the before is less than 0. We want the difference to be less than 0. We don't want there to be a difference. By default, then, the mean difference is greater than or equal to 0. Step 2 is to identify the players, which in our case is the raw data that's given to us in this table. We also need our alpha, which is the 5% or 0.05. So I've got to enter the data into Minitab. Now I can use a worksheet that I already have. I'm going to go over here to column 4, and I'm going to put before hypnosis, and I'm going to put after hypnosis. Okay, I could put the subject number in there, but I don't necessarily need it. Okay, so let me see if I can find the numbers here on my paper so I can type them in. So before hypnosis, we had okay. 11.3, 8.1, 6.3, 11.6. And then after hypnosis, okay, so I've entered the data. We're doing a paired t-test. It's stat, basic statistics, paired t-test, paired t. Sample 1, in this case, remember sample 1 is our after. Sample 2 is the before because of the way the question was worded. Sample 1 is after, sample 2 is before. We're using a 95% confidence level. My hypothesized difference always defaults to 0, and we are asking if it is less than. I click OK. And I click OK again. Now, should you need it, again, Minitab calculates the descriptive statistics for each sample. I had 8. My after mean was 5.588 with a standard deviation of 2.608. It's there in the results if I need it. I also have the estimation for paired difference if I need it. What I need is the test with my t-value and its corresponding p-value, which I forgot to write over here as step 3. Okay, so step 3 is to calculate the test statistic, which is a paired t and its p-value, which we've done in Minitab. Oh no, where did it go? Okay, let me get this copied. Oh, you're doing something wonky on me, ain't you? Okay, it's way up here, guys. I don't know why it's way up here. Let's see if it'll let me move it. Oh, I see the problem. Hold on just a second. Okay, so my test, let's undo this. My test value is -304 and my p-value is 0.009. Again, you need to record those. So my t-value is -3.04. The p-value is 0.009. Then we move on to step 4. I sound like a broken record because step 4 is we're going to make a decision by comparing the p-value to the level of significance. The p-value, which comes from Minitab, is 0.009. My level of significance is 0.05. I'm going to make the comparison. 0 to 0, 0 to 5. 0 is less than 5. So P is less than or equal to alpha. When P is less than or equal to alpha, we reject the null hypothesis. If we reject the null hypothesis in this particular problem, that means that the mean difference is not greater than or equal, that it actually is less. We reject the null. Remember, that means the null is false or invalid, and the alternative is true or valid. And so the question originally was, are the sensory measurements on average lower after hypnotism? So we have shown that the mean difference is less than 0, which means it is lower, or in other words, hypnotism does seem to help with a person's pain level, okay, based on this information. So we write a conclusion. We would say at the 0.05 level of significance, the sensory measurements on average are lower after hypnotism or after hypnosis. Hypnosis. Do we always use the post-change data in Karsten? You have to read the question the way this one was worded, because you were interested in what happened after hypnosis, after became your first sample. But if you go to another problem, and I don't know that I have time to work through the whole thing, but if I went to this other problem, this one is that says there's no mean difference between actual and forecasted. So in this case, the way this is worded, I would put actual as my sample 1 and forecasted as my sample 2. So it all has to do with the way the question is worded. You have to read them. You have to pay attention to the details. The words, every single word is important. Okay, so that gets us through the two mean t-test, both independent and dependent. And we've gotten through the parametric test, Mann-Whitney, which relates to the independent t. I have 8 minutes, and I cannot do the Wilcoxon signed rank in 10 minutes or 8 minutes. I will double check again to make sure there's not any of those on quiz 8. If there are, I will make an adjustment to the due date. And if we need to, we will come back and visit Wilcoxon signed next Tuesday, first thing. Okay, you have your mini project 3 on normality that is due on Monday. Again, right now, quiz 8 is due on Sunday, and I will double check it. If I need to make adjustments in the due date, I will, but otherwise, right now, it is due on Sunday. You may also want to start working on project 4 in case you have questions next week before the due date. I would at least take a look at the instructions so that if you have questions, you can ask them.
I already had a question lined up for the next project. All right, so my question is, was me filling it out as the question was asked, was that appropriate for like the way I fill it out, or does it have to be like a written paragraph? Because I felt like it could have been better identified if I just filled it out.
Don't think I understand your question, John.
All right, so when it was like display your sample mean, and then I put the answer right next to it, I'm saying, is that okay to do and then paste it?
You can paste it in, but then you need to either, ideally it would be better if you say the sample mean is, make a complete sentence, the sample mean is blah blah, and record it. Is that what you're asking me?
Yeah, because I didn't know if me just saying the number was satisfactory over me writing a sentence.
I mean, it's okay, but a sentence is better.
Okay.
Other questions? Okay, I will have Zoom office hours on Thursday. I will probably move them to 1 to 3 because I'll need to pick my daughter up at school at 3:30. But I will be in Zoom from 1 to 3 on Thursday. Should you have questions, and again, I'll try to take a look at quiz 8, and if I need to make an adjustment in the due date, I will. Otherwise, it is due Sunday. Mini project 3 is due on Monday. Karsten, you have a question?
It's about quiz 8. Is that okay?
It can be, yes.
Okay, so scenario 2, it says the before values is matched to an after value. Would that mean the before value would be the first sample?
I would anticipate the answer being yes, but hold on and I will pull that up and look at it for you. You said scenario 2?
Correct.
Well, the way the table is set up, you have your before, which is the kind of the middle row of the table, and the after is there. Let's see, effectiveness in reducing failures. Okay. So you want to reduce the failures. So your after would be sample 1 and the before would be sample 2. Because because again, look at it. It says test the effectiveness of a software patch in reducing system failures. So you're interested in what's happening after you apply the patch. It's kind of
So
just
you-
like that problem we just looked at.
So you want to measure a reduction as a negative number, not as a positive?
That's fine. That
Okay.
would show a reduction. Yes.
Okay, thank you.
You're welcome. I got 4 minutes. Other questions? Okay, then, guys, I will see you next Tuesday. Again, if you have questions, I'll be in Zoom or monitoring emails.